talked about not recording. So we talked about electromagnetic oscillators and the energy stored in the electric field via a capacitor, and the energy stored in the magnetic field via an inductor, right? And we saw how the current could form into an oscillator going one way and then going back the other way to get back to its original value and sort of forming this back and forth oscillating loop. All right? And we can see this in changes in magnetic potential energy versus electric potential energy in these bar graphs, right? So hopefully you remember reading these energy diagrams from Physics 1. And then we see the current direction, how it goes around the circuit. First it goes around one way, and then it sort of peters out, and then it goes the other way. So you can think of it as like unwinding and winding, right? And then it just sort of does this back and forth. So we talked about one of the things we have to talk about from those oscillations is the charge and the current, right? So we saw over here in this slide, not in this slide, I don't even know where I am anymore. We saw over here that that using our energies, right? We could first consider a solution, right, where the energy is there's no driving force or sinking force, right? There's no loss and there's no gains. So in that case, the energy is constant, or we could say that du dt is equal to 0, right? So when you do that, this part becomes 0, and you get this differential equation. Now, recognizing that I is equal to dq dt, we know this from definition, we can write di dt as equal to ddt dq dt, and that's going to equal the second derivative of q with respect to t. Okay? And so plugging this term back in to this term, we get our harmonic oscillator equation for our LC oscillator circuit. Okay? And again, with differential equations like this, the real trick to them is to know the solution. So the solution to that differential equation for Q is this term right here, this time-varying function. You notice this big Q is the maximum charge, right? That's the amplitude charge. And then you have a phase. You have omega t plus phi. So you can, from here, you can find the current directly by just taking the time derivative, right? And you get that the current will be equal to omega q, or that frequency, times q, times sine omega t. All right? And you'll notice you have a minus sign because the derivative of cosine is minus sine. Okay? So what we have here is if you want to check that this is a solution of the differential equation we just talked about, you want to solve for q, solve for dq dt, and you're going to want to take the second derivative of this, right? So let's do that. Let's calculate di dt, just for poops and giggles. So di dt is going to be minus omega squared q equals cosine omega t plus phi. All right? So what you can do is you can plug this equation, all right, back into, you can get those two terms, and you can plug that di dt term here, and you can plug in the q term here in this equation, and you'll find that when you multiply everything out, that it will all equal 0, and keep in mind that omega squared will be, let's go forward. We want to keep in mind that omega squared will be equal to 1 over LC, right? We saw that from last time. Nope, that omega squared will equal 1 over LC. All right, and you'll see that everything pops out and goes to 0. Okay? Okay. That's the first method of solving those diffie-Qs. So we did this checkpoint last time, and now we want to talk about a little bit about electromagnetic oscillations. So the electrical energy stored in an LC circuit at some given time is given to UE equals Q squared over 2C, right? This is from earlier in the semester. But now we need to put that whole function in, and you'll notice we get a cosine squared function. Now, the magnetic energy will be equal to the same thing, but times sine squared. And I want to note that this is easy to derive, this is difficult to derive. But if you look at the graph, all right, this is where we can be a little tricky, all right? This is where your mathematicians might suffer here. If we look at the graph, we can see here that we have our electric energy, right? And it goes like a sine function. We can see the wave, right? Like that. Now, what's cool about this is that the total energy, hold on, let me change the color there. What we know here is that U of E plus U of B has to equal a constant, right? And we can tell because if we look back at our first, we want to go all the way back here. When we look at this set of pictures, we know that the only two energies are the magnetic field potential and the electric field potential, right? So we already know that there's situations in which the energy can either be all electrical or all magnetic. So when we go back to our energy diagram, we can see that UE max, right, will equal Q squared over 2C, but we also know that that's the total energy available to the magnetic field. All right, that's by conservation of energy. That's it. And that is going to equal UB max. All right, so knowing that, and knowing that UE, so we know that UE plus UB always has to equal the maximum energy, right? Q squared over 2C. All right, so knowing that, we know that if there's 0, that when there's all the energy is in the magnetic field or the electric field, none of it's in the magnetic field, right? And we notice that they peak at opposite times. They're out of phase. And because they always have to add up to 1, you can say that, and they look the same. You'll notice you have this expression here. You can it's like by inspection practically, but you can say, it's easy to argue, oh, well, UB has to equal Q squared over C times cosine squared of omega t plus phi, but minus pi over 2. All right? And that minus pi over 2 allows us to say, that's just Q squared over 2C sine squared. This is just trigonometry. Omega t plus phi. All right, and that's how we can develop this expression. But you'll notice we use conservation of energy and start with something easy to arrive at an expression for something that is difficult to arrive at. Okay? So, hopefully that makes sense with the energy oscillations. You'll notice when you add these together, you have the same maximum. You have the same total energy, right? So when you have these here, you have QT, you have the same, hold on, I'm going to erase this stuff. You have the same amplitudes, right? So you can factor those out, and when you add UE and UB together, you get cosine squared plus sine squared of the same phase. That just equals 1. And you indeed get a constant. So everything holds up. Okay? So, and did anyone think of any questions from yesterday about this stuff, or does any of it make a little more sense before we move on? Because I know there was some struggle yesterday with this stuff. Everyone's good? Okay. Sure. So which process, though, specifically, Lewis? Just the energy, or the energy process and the LC circuit? Okay. So let's take a look at it again. That's no problem. It's one of those things we could probably see a few times. So let's look at these circuits, all right? So I want you to just focus on circuit A. So what we have here is a charged capacitor and an inductor, all right? And so essentially in the closed circuit, if the capacitor is charged and there's a load here, right, the capacitor will start to discharge. We saw that with RC circuits too, right? You need, if you were charged to a battery, you were charging. If you charged it to a resistor, the capacitor would discharge through the load. All right, and so that's what we see here. So when we look initially, all the capacitor is charged, all the energy is electric. Okay, so as the capacitor starts to discharge, we have a current that goes through the circuit. All right, and as that capacitor is discharging, that current is changing. So as that current flows through and goes through the inductor, that change in current leads to the buildup of a magnetic field, because you have the current is going from 0, it's increasing, right? So you have an increasing current and you have a buildup in your magnetic field, and the energy is decreasing from the capacitor. It's decreasing and going to the inductor, right? We're losing energy from the electric field and gaining it in the magnetic field. Now, eventually we have all of our charges being discharged, and we have our maximum current. That occurs here, and we've built up our field, right? So then all of the energy has left. You'll notice there's 0 energy here, and all the energy is in the magnetic field. Okay, so by the time we get to C, all the energy has transferred to the inductor, to the magnetic field stored in the inductor. But now, as time goes by, right, that maximum current is flowing, but now that maximum current is going to start to decrease. So that will lead to a decrease in our field here. And what's happened? Where's the charge going? Well, the charge is building up, charging the capacitor, right? So the energy can transfer from the magnetic field here back to the capacitor, from the magnetic field to the electric field, and by charging up the capacitor, we're decreasing the current and thus lowering the field in the inductor. Okay? Until eventually we have I equals 0 again. And all our energy is electric. Now we want to kind of pause here before we start going the other way. We want to notice something. Our current, this oscillation is very different than a DC circuit, because in a DC circuit it goes up. You know, DC circuits, it goes up or it goes down, right? But it doesn't do both. Here it's going to oscillate. It's going to be like a sine wave. Okay, that's more what we have here. But I want to point out a few things at, yeah, we're getting to AC. So this is much more than, this isn't AC particularly, because remember, right now we don't have a battery of any kind. This is just an oscillator. AC requires an AC battery, which we'll draw on circuit diagrams like this. So you'll notice that's not in the circuit. So, all right. I want to delete some stuff and keep some stuff, but I want you to look at, we're right now at figure E, and I want you to look at figure E, and I want you to notice some things between figure, you know, so we want to just look at the current, because there's current and energy and fields. All right, so let's go back through the process just concentrating on the current. So as the capacitor starts to discharge, you know, your current flows from negative, your negative stuff will want to go around the circuit. And remember that the current is always opposite the flow of charge. So the current one goes from the higher potential to the lower potential. So the current will go around counterclockwise, right? And we have a growing current until we get to C. All right, so this is where the current peaks, and then because there's nothing to draw from anymore, it starts to decrease and charge starts to build up. So now the current is still flowing in this counterclockwise direction, but it's decreasing, and then we get back to a minimum. All right. However, you'll notice that the capacitors are opposite, the polarity is charged, right? This plate is now the low potential plate, and this plate is the high potential plate. So when we go to set up current the next time, the current will now go clockwise through the circuit. It will increase and decrease and go back to the same thing. But then when we reach the figure after H, it's the exact same setup as A. So you could almost say that one way to look at this is that this is figure I and A, and that figure I is the same as figure A. All right? So that lets you sort of delete that I and just say, okay, it's figure A. All right, but now we notice, going back to how the energy is transferring, again, just like before, we're losing electrical energy to the magnetic field till the magnetic field, the energy in the magnetic field maxes out, and then we're losing magnetic field energy back to the electric field as we go charge the capacitor again. Okay? So does this part that I've made sense, at least, does this part I've explained just here at least make a little more sense? Are we a little better today than we were yesterday? We've kind of put a lot of stuff together very quickly. Okay. All right, good. So we're not done quite yet. I still want to go back to that slide that we just talked about, because it's important for building up everything, for not getting lost in the rest of it. And where am I? Just navigating this stuff is becoming tiresome. So again, we looked at the differential equations for oscillation to get the trajectory of the charge, right? Which also gave us the current. And what we could do there, we can see how charge varies and how current varies, and now we can see how the electrical energy varies. And what we did here is we just looked at the very simple expression for the energy, right, of the electric field. But instead of recalculating for UB, we just used the conservation of energy to derive this expression. All right, so this expression can be derived simply from the conservation of energy, or more non-trivially through other means. Okay, and you can notice that the total energy always has to add up to this baseline here, right? Which is that this is that Q squared over 2C energy, right? And if you add both the numbers, no matter where they are, they'll always add up to that number. Okay? So let's go on, and we want to talk about, I think we talked a little bit about this yesterday, but we won't spend a lot of time on damped oscillators, but we can use the energy, our energy our energy equation to add damping. So we saw before, no, I mean Tuesday. Yesterday is always last time we met. Tomorrow is always the next time we meet. We only meet on Tuesdays and Thursdays. I'm old, so you will have to forgive me. My memory. Yeah, that's all there is to that. I don't know. Days are starting to flood and compact in ways I don't understand anymore. So last time we saw that, and even today, we started off with our conservation of energy to develop our equations, right? Our oscillator equations. Now, in an undamped oscillator with no sources and no losses, when we took the derivative, du dt, that equaled 0, right? But now we're going to say, well, what if there's a resistor in this circuit, right? What if we have loss? And that's usually what we have with heat. You'll notice that gives us now an L, a C, and an R. So we've got all of our major circuit elements. Well, if we are losing power thermally, then this is no longer true, and the case that we work with is du dt equals minus IR squared. Why is it minus? Because we're losing power, right? Thermal, when we're converting, the energy here is being lost to heat. So the minus means you're losing energy, right? And so when you do that, you can take the derivative of all these equations, and now instead of setting them equal to 0, you set them equal to minus I squared R, and you rearrange everything in terms of charge, just like we did before, right? Because I is equal to dq dt, and you get this second order homogeneous ordinary differential equation, which you'll notice is similar to what we had before, but now we have a damping term in it, right? So that term will be responsible for the damping, and when we solve it, you'll notice we have our cosine part, like we did before, and we have our amplitude, but we have now this dampening part, right? And in this dampening part, you can see that as t goes on to infinity, you have your amplitude shrinks to 0. So essentially what this looks like, if you've ever seen it, and I wish I could draw a little better, you'll have sort of your cosine will be in this envelope, and it'll look something like this. This is not perfect, but I'm doing the best I can. And you can see that that exponential decay rapidly shrinks and converges, and it squeezes down your amplitude of your function. But you'll notice that you have on omega prime, so omega prime will certainly be in terms of the original omega, but it'll also deal with this part of the exponential. And keep in mind that just like we had before, omega equals to the square root, or 1 over the square root of LC, which means omega squared is equal to 1 over LC. That'll be used sometimes more frequently. So all we're doing here is adding in a damping term energetically, right? And when we do that, it gives us pretty much right away a new ordinary differential equation to solve. And again, if you want to prove this is a solution, that Q is a solution, you just take its first derivative. You have Q, plug it here, plug in dq dt, plug in the second derivative q dt. You'll add all of them up and you will get 0. All right? If you don't believe me, I'll leave it as an exercise to the student. But all we've done here is start with energy conservation and then develop an ordinary differential equation and solve it. That's all that's happened here. So now we want to get to AC, we want to start building up to AC circuits. So an AC circuit, in a way, is a forced oscillation, right? You're driving the circuit with a voltage that is alternating. Now, why would we want to do such a thing? Well, there's a few good reasons, all right? So if we read here, it's a busy slide, but you can see you have a circuit or a wire that's free to rotate in a magnetic field, and it creates friction on these slip rings. All right. So we can see here, as we'll read this part, as the current alternates, so does the magnetic field that surrounds the conductor. This makes it possible for the use of Faraday's law of induction, which, among other things, means that we can step up or step down the magnitude of an alternating potential difference with transformers, which we'll see later in the chapter. Moreover, alternating current is more readily adaptable to rotating machinery because it itself rotates, all right, than non-alternating current. And this is important. Rotating machinery can create things like generators. Like generators are rotating machinery. And so that's what you can do here, is you can put this here with these slip rings. The AC mechanism will cause friction on these loops, on these wires. That friction will send current along the wire. And that's basically how your current is generated. Now, when you, for my electrical engineers in here, you will study polyphase power transfer, which is not possible with direct current, but is possible with AC current. And this allows currents, you know, in the old DC current setups, it's a bit like 5G. They thought there would have to be substations like one every mile in every direction. And with the wires to go into homes, this was not really workable, or as workable as people thought. And so one of the big issues with DC was energy transfer. But the ability to step up and step down voltages meant that you could step up to a large voltage and make a little tiny current, and that your tiny current would only be the source of thermal losses in your wire. This allows you to transfer power over miles, tens of miles instead of tens of meters, instead of hundreds to thousands of meters. So it was it's a huge development in sort of our ability of the modern world. And it's really, really, important to modern technology. So one thing we want to know about forced oscillations is that whatever the natural frequency omega of the circuit may be, forced oscillations in the circuit occur at the driven angular frequency. So you're going to see, I try to talk about this a little bit. When you build a circuit, an LCR circuit, it will have a frequency, a resonance frequency. So that's a property of the circuit, but the actual omega of the circuit, of the output of the load, will be whatever it's being driven at. All right, so you have to be careful of that. Now, interesting things might happen when omega d, when your driven frequency equals your omega frequency. That need not always be the case. Okay. So, moving forward. So we want to look at 3 simple circuits to understand how in these alternating arenas, because we just saw that there's delay between the capacitor and the resistor, right? Not everything's loading at the same time. So we want to look at these 3 simple circuits and analyze them, and then we'll use them to build up our total RLC circuit. So the alternating potential difference across a resistor can be described by Ohm's law. right? We have that right here. So V equals IR. We can see here in the graph, if you have this frequency, you'll notice this is what the alternating current looks like. And we have our resistor, we have our IR going through the resistor. Now, the angular frequency, right, will be from the source. All right, it will be that driven frequency. And what we can see here is that the voltage and the current are in phase, meaning they both peak at the same time in these types of circuits. Now, many, many moons ago, you might have done phasors. We might there was a section on phasors when we talked about waves. So that might have been like the first week of class. And phasors can help because they sort of, instead of having a long multi-oscillatory track, they just move around in circles, right? And if the two objects line up, they're in phase. And if they're out of phase, they'll have different angle between them. And that'll tell you very quickly how out of phase they are. But the problem with phasors is that the math looks a little intimidating, because here, for figure A, you have something like I is equal to IR cosine theta, or cosine omega t, right? In the phasor notation, if you want to write it out mathematically, I is equal to I naught times e to the minus I omega t, right? And you have to convert these, you'll have to understand that these are equivalent representations. These things aren't equal to each other, but these are two ways of looking at the current function. This ends up being easier to analyze once you know how to do it. But for right now, it's not developed usually until you get to differential equations. So for right now, we'll stick with our cosine functions. But the phasors geometrically, if you see one written down, are easier to read right away. It's easier to see phase differences. So, okay. So it talks about angular speed, the length of each phasor. So we're talking about phasors, projection of each phasor. Yeah. So I'm going to tell you that you can look at the phasor properties. That's something I will leave you to look at on your own if you'd like to. It is okay to stick with this representation if you're getting even further lost. That's one of the reasons I don't want to like to build on phasors, is it's already so easy to get lost after that, you know, piling on more seems gratuitous, but we don't have to do that. Now, this is, hold on, something got messed up here. All right. So I want to be sure they got this right for an inductive load. Yeah, so they just got the wrong circuit here. So for an inductive load, you don't have a capacitor. You have an inductor, L. So cross all that junk. And we'll change that to inductor. I don't know how I missed this when I was prepping this stuff. So now when we look at a inductive load and a capacitive load, we're not going to be able to use Ohm's, we'll be able to use something similar to Ohm's law, but not with capacitance and inductance directly. What we'll have is something called the reactance. We'll have a capacitive reactance and an inductive reactance. Now the inductive reactance is going to be the product of the driven frequency, right? So the frequency of this thing right here times the inductance L of the circuit. Okay, so part of it's from the driven part of it's from the circuit. What this will do is allow us to look at the voltage across the inductor in terms of, the unit of reactance is ohms. So we'll be able to use an Ohm's law sort of version of this and say that VL equals IL times XL, where XL is that inductive reactance. Now, when we look here, we have, for an inductive load, you're going to notice that the current peaks after the voltage, right? So the voltage, one way to say here is that the current lags the potential difference by 90 degrees. And you'll see here you have the voltage and IL there. The voltage peaks first, and then the current peaks, right? This happens at a later time. That's the other thing, is you're looking at this and you have to say which one peaks first. The voltage peaks, and then by 90 degrees, they're out of phase by 90 degrees, then the current peaks. All right? In the phasor diagram, you can see you have all that stuff to look at with phasors, and that's a pain, but you'll notice it's much cleaner, right? You can see the voltage here, and you can see that in a more sort of natural way, you can see the current lagging the voltage. All right? So sometimes this will be called an Eli circuit. All right? Because the voltage leads the current. So that's supposed to be squiggle. That tells you what it does. And that's the current, right? The electromotive force will lag or lead. They both start with L, but it comes before, right? Leads I. Now, if we look at the capacitive circuit, so you'll notice here, we'll just have to cross that out. We'll make this a capacitor. See? All right, you'll notice X sub C is equal to 1 over omega D over C. So you'll notice the capacitive reactance, again, will give us this quantity in terms of ohms that allows us to look at the voltage across the capacitor, and it's just I times that capacitive reactance. But you'll notice that the reactance does depend on the capacitance itself in the circuit, and the driven angular frequency of the forced voltage source. Okay, so as we can see here, you're going to want to notice the current now peaks before the voltage, right? So one way to say this is that the current leads the potential, and lead here means that the current peaks at an earlier time than the potential difference. And these are often called ICE circuits. Right? It's capacitive, and the current peaks before the EMF. That's what, yeah, so for Eli, now I'm feeling stupid. This was for inductance. And in an inductor, the potential peaks first, and in a conductor, in a capacitive circuit, the current peaks first. All right? Mixing my metaphors here. That's all right. It happens frequently. Okay, so when we put them all together, we get the series RLC circuit. All right? And that will give us the machinery to analyze this, looking at those three circuits to analyze this big circuit. All right, so before we do that, let's take a break. It's a good time to take a break, even though it's a little early, but we started a little late, but we talked a little bit. But this is sort of a good chapter to wade through and marinate through. I don't mind. And we do have some examples coming up before you all freak out. So they're coming up soon. I think I have a few examples actually. I wanted to do examples on applications because a lot of the examples for the RLC circuit will sort of cover a lot of stuff we use. I think I put in a resistive circuit, a driven one, to make life a little easier. Did I put in an RLC? Hold on. Yeah, no, I put in an let me see here. Good. Yeah, I put in an example after we talk about power. So we'll talk about the series circuit, and then we will, when we come back from break, we'll cover that stuff, and then we'll finally do some examples with it too. So those are coming right now. So anyway, let's meet back around 5:02, around maybe 5:02, 7-ish, and we'll get started then. So I'm gonna I'm going to be away, but I'll be back soon. I realized one of my examples was out of order. So before we start the go crazy with all this and you're driving yourselves mad, we are going to want to do one quick example that I need to move in my future versions back. So that's what we're going to start on when we come back. And that'll hopefully make the previous stuff make some sense. That was supposed to go there, but did not. So we have an example. All right, I'll be back. I'm back. All right. Okay, so let's work through this example, which I think will be more instructive. So it's really, a lot of the questions here are really basic. It's just sort of, do you know how to put together what you need, or don't you? Okay. So we're given here that we have a resistance of 200 ohms, right? And a sinusoidal alternating EMF device operates at an amplitude of 36 volts, and FD equals driven force equals 60 hertz. So we want to know what is the potential difference, because we'll have a potential difference, right, over time across the resistance. Now our loop law should tell us that if we have the EMF, if we start here and we do plus epsilon, right, we'll have minus VR. Both of these are functions of t. Let me do it again. If we use the loop law, right, we'll start at a corner. We get to our EMF. That'll be a function of t here. And then we go and we get to our resistor, right? So that'll be minus the voltage across the resistor. We don't know what it is. And then we get back to our original point, so that's going to be equal to 0. So we can see here that ET is going to equal to VR of t. So now all we have to do is construct epsilon, or not epsilon, but the electromotive force as a function of time, right? So we know that this will be equal to, in symbolic form, is E naught, right? Cosine omega t. We're just going to assume phi is 0. Okay. Actually, is cosine correct here? Let's see. I don't know if it makes a difference whether it's sine or cosine, but right. So we might want to, well, these should be in phase with each other, right? I'm just trying to see, do we have a convention here? I'm just trying to see, because I usually just figure it's sine or cosine. What did we have here before? We have to go back. I want to make sure I'm being consistent. I worry about the consistency. All right, so if we look here at the load, and we're looking at VR, I was worried about being sloppy, and it came back to bite me in the butt. So you'll notice that VR, if you look at our graph here, and we want to be consistent with what they say, that VR is actually a sine function. I knew it didn't quite look right with the starting at 0. And this will give us the whole lag, non-lag thing we like. So going back to our example, right, we want to, we noticed, again, we'll write down that E sub t is equal to V of t, and that E of t is equal to E naught, or E max rather, sine omega t. All right. Now we want to find, we have that EM is equal to 36 volts, and we need to find omega is equal to 2 pi times FD, and that will be equal to 120 pi. I just multiplied 60 by 2. So you can write that your EMF is equal to 36 times sine of 120 pi times t. All right? And we know that since these two things are equal, we can write that VRT, VR, will be equal to 36 sine omega t. Okay? So, and this makes sense because we're talking about electricity here, right? As soon as we turn on the circuit, it doesn't just start at a maximum value, it starts off at 0 from off, right? And then when we turn it on, we would expect it to either build up or start oscillating in one way or the other. But as soon as we turn on that switch, the value is 0, so sine, I think, does make more sense. And that's why when I was being cavalier with the cosine, I had to stop because things weren't adding up. So, and then I was glad I found that graph in our previous exploits. So, this is the answer for A. I want you to notice there's virtually no math in this problem at all. Forgot a parenthesis. That's okay. All right. All you're recognizing is that the voltage across the the voltage, the EMF across the source, the driving force, or the driving source, is the same as the voltage drop across the resistor. That's it. Once you recognize that, you know the form of this driven force. You have it right here. And then all you have to do is plug in the particular numbers, and you're done. That's it. So, it almost seems, it seems deceptively easy, right? And then if we look at part B, it says, what is the current in the resistance and the amplitude of IR? Well, we know that V, right, V equals IR. So all we have, we have I equals V over R. So we have, what, is that coming from my house, or? That's got to be coming from outside. That's weird. Or downstairs. I don't know. Anyway, so that is going to be equal to 36 over 200 is going to be 1.8, I believe. Yeah. Sine of 120 pi t. All right, and there's your current. So that'll be in amps. We don't want to forget the units here, right? Volts. Oh, that is coming from outside. Okay. So, does that make sense? Does anyone have any questions on that in particular? Was it 100? Oh, crap, it's 100. So 0.18. That point's got to be deleted. More fun math mistakes with Dr. Toland. 0.18. There we go. So basically, you'd find the inequivalent resistance where you can, and then you turn, if you just had one source and multiple resistors, I just turn it into a multiple resistance problem, and you'd probably have to break it up from there. I don't usually assign problems like that here, though, because the point is more the RC and L's working together, and that kind of gets yucky when you start mixing in multiple types of circuitry there. So you can also do this and ask the same questions for the capacitive circuit and the inductive circuit, and it's pretty easy stuff. So you know, you wanna be able to look that up and do it. Let's go and talk about the RLC circuit. Okay. So the RLC series circuit is really what we're going to focus on. So we're not going to, there not going to be problems where it starts getting, where you're adding all sorts of different elements in different places. That would make it a very hard problem. We're just going to stick to our simple setup of having a resistor, capacitor, and inductor in series, all right, with an alternating current. Now you'll notice the current itself is alternating, so this is only a part of it. First it goes one way, then it goes the other. It goes back and forth. It's sort of this push, pull, push, pull, push, pull. All right, and you'll notice we define again, when talking with power and starting at 0, right, the sine function makes more sense, and the current will be given by, will also be given by the sine function 2, but you'll notice it'll have a phase factor. All right, that phase factor is not arbitrary. That phase factor is a part of the circuit. And the current will be in phase or out of the phase with the voltage, just like we saw in our 3 circuits. Remember how the inductor and the capacitor led to the current and voltage peaking at different times? We just saw that. So this phase will be due to that. But there are important things we have to see and that we'll look at. So the current amplitude is given by this form of Ohm's law that includes both the resistor, the inductive reactance, and the capacitive reactance. I want you to notice that it's the difference of these things here. All right, that's under 1 square, and you have r squared here. It's tempting to write this underneath the root that as r squared plus xl squared minus xc squared. This is wrong. Don't do it, okay? Bad. We don't want to do that at all. Notice the parentheses. Here and here, and the squared here. Now, this quantity will be called the impedance. You'll notice it'll be given with this letter Z, and this allows us to write Ohm's law for AC circuits as V equals I Z, or Viz. All right, but you'll notice that in order to analyze these circuits, you'll have to know the capacitive and inductive reactance, and you can look at the current, if you will, in terms of the capacitance and inductance by remembering that the inductance or the capacitive reactance is equal to 1 over omega c, and the inductive reactance is equal to omega times L, driven omega times L. All right? Now you'll notice something very interesting. Well, you might not notice it yet, but it's possible there will be a special case when XL equals XC. And this will be the condition for resonance, or when omega driven equals the omega of the circuit. Okay? So from the phasor here, you can justify the equation here, which I'm just going to sort of state, which is that phase angle is equal to XL minus XC over R. You can also do that from the Pythagorean theorem. If you notice, since you have your impedance, right? If Z is equal to R squared plus XL minus XC squared to the 1/2, right? You can look at this as the the y and the x components, and then you can use the tangent, the opposite over adjacent from the triangle. So what they essentially do is they build that up here, right, where they have your resistance and your VL over C. Where's the triangle? I'm not even going to try and do it with the phasors, to be honest with you. It says from figure D, from the right-hand phasor triangle, we can write that tan of this angle is equal to the opposite. Yeah, the opposite, which is going to be this angle here. That's VL minus C over the adjacent. That's going to be VR. So that's where you can get this from a voltage, and then you can use the Ohm's law, IXL. The currents cancel, and then you get this expression. But it also makes sense here for your X and Y components that you normally do. Now, so that's what I mean by phi is not arbitrary here. It's very much a part of the circuit. We have to keep that in mind. And oh, it's going to start raining. Oh, it already rained. So resonance, we already discussed this. That's when XC equals XL, our capacitive reactance, equal to our inductive reactance is equal to our capacitive reactance, and phi will be 0. Okay, you can see that because this part goes to 0, and then you do the arctangent of 0 is 0. Okay, so good. All right. So why don't you, so let's work through this example, and you're going to see that there's more that we need to solve. So I'll do some of I'll sort of get you structured, and then I'll let you sort of finish it off. All right. So we have these given values of R, C, L, FD, and our electromotive force. All right. These parameters were used in earlier problems. So we want to know what is the current, the amplitude current. Well, we know that the current amplitude, we can write V equals I Z. So you have V, right? And now you need to solve for Z. Right? So the first things you need to do is you'll notice you have R, but you need to find XL, the inductive reactance, the capacitive reactance, and then once you have those, you can find Z, and then once you have Z, you can solve for I. So that's the structure of the problem. See if you can apply it and look back through your notes and see if you can solve those things. Okay? It'll be good practice for you to do it. And I'll give you about 2 or 3 minutes to get started, and then I'll sort of fill in the blanks and then let you sort of move on. So right now you want to practice on finding XL and XC, capacitive reactance, capacitive inductance. See if you can look those up or go back. I don't know if any of you are taking notes, but you can't unfortunately rewind this movie until later. Okay, so remember, x sub L is equal to omega driven times L, and x sub C is equal to 1 over omega driven times C. From there, that should be everything. So try plugging those in and making sure you get used to them. All right, what did you guys get? Were able to solve it? You should have gotten around 86.7 ohms. There, you should have gotten 177 ohms. It's a 6. For these two, right? And you're already given R. So once you do that, you can get Z. Of 200 squared minus squared, and that will equal 219 ohms. And then once you have Z, I equals V over Z equals 36 over Z is 219, and that's going to equal 164 amps. Okay, so that's how you would solve that problem. It's pretty straightforward. You just have to know, you just have to follow the structure here, and that'll take you right to I. Okay, now for part B, you just remember that tan phi is equal to XL minus XC over R. And now that you have all three of these numbers, you can get phi, and you should get phi is equal to about negative 0.424. I'll make this a 0 and put the negative here in case anyone's confused. Hold on. Let's make this cleaner. .42. Okay. Radians. All right. So omega d, right? The driven omega is equal to 2 pi times the frequency driven. So that's going to be equal to 2 pi. Frequency driven is given right here, right? So that's going to be equal to 120 pi. Okay. No problem. Okay. So all right. So let's go on. Now, what's interesting, or at least not of particular, it's not particularly obvious, is the power. All right. So when we take power, it's hard to look at the power at any one given time because we're used to looking at, for DC currents, right? We're used to power being equal to I times V. But if you look at the current and the voltage varying at any given time, they have a power. So it makes more sense to look at an average power, but there's a problem with that. When we look at averages of our voltage, right? If we just look at I average and V average, that could be a problem because both of those will be sine or cosine functions and they average to 0. And anyone who's plugged into an AC outlet knows that the average power is not 0. So over one complete cycle, while we have that average is 0, the average value of sine squared is 1/2. If you look here, this is a sine squared function. Instead of looking at that, we get a 1/2. So it's easier, instead of using this form, or it's more instructive, instead of using this form of power, right, to use the ones with the squareds. So if we say that the average power is going to be equal to I squared R over 2. You'll notice we can look at, because I is proportional, right? Or wait a minute. Let's explain what, hold on. I'm just tired. So this 1/2 will come from, and I didn't even have the squared. We can do this because the I squared will give us the sine squared that we can average. But we want to look at this in steps first, okay? So the power from here, from IV, we can rewrite this as I squared R, right? You can play with Ohm's law and see that. Now, when we have a sign varying power, we'll get this squared, and the power itself, the instantaneous power, will be I squared times R times sine squared omega t, hence the sine squared curve here. Now, when we take the average of this, instead of averaging to 0 like I or V would individually, like you see here, you can get this 1/2, that's where the 1/2 comes from, by averaging the sine squared part of this. All right, so the average value of these constants is just the constants, so you get I squared V, and what you'll notice is that they call this the root mean square power because you can make it look like, you can sort of make it look like a current term squared times a resistance, and if you define this as the root mean square current, you'll notice that the average power looks like the DC power, but now it's just in terms of this RMS current. All right, so let's look at that again, because there's a lot going on and I had a little bit of a brain fart. So again, we want to start at the top, right? And I know it's a busy slide, but we want to start off with our, with our definitions of power. Equals IR, IV equals I squared R equals V squared over R, right? So those are our DC powers and the forms we wish to keep if we can. So when we do this, the ones with the squares will be ideal because they allow us to have a trigonometric function that lets us average to something that's not 0. Whereas if we have I as a function of sine and V as a function of sine, and we average both of those sine functions, well, actually here we'd get sort of the same thing because it would be sine times sine because they're both sine of the same phase. So that could work too. But this works and is a little more direct without worrying about two different types of quantities. So it'll just be easier to deal with. So we multiply the I sine omega dt minus phi, and we square it, and that gives us this expression. All right, so hopefully that's simple. We're just plugging it in. When we average the constants, we just get them back, right? So that's why you'll notice in the average, when we average it, we just get I squared R back. But when you average sine squared of phi, you get 1/2, which you can see right there. So all of this, when you average it, goes to 1/2. All this sine business. Okay, and that's where the 1/2 comes from here. Now, 1/2 can be written as 1 over root 2 times 1 over root 2, or equals 1 over root 2 squared, right? Now we do that because it lets us define a new quantity called IRMS. You'll notice that's defined here as I over the square root of 2, and we now have this the ability to write this RMS current in terms of the average power. We can say that that the average power equals IRMS over root 2 times R, and we have an average power for AC circuits that looks a whole lot like our power for our DC circuits. We do have to keep in mind that, and you should see that the RMS value is not the peak value, right? If you peak at 6 amps, for instance, your RMS value will be lower, but again, we're getting an average power, right? Not peak power. And the peak power only occurs at one time whereas the average can give you the average power over any time, okay? Or at least over one cycle. Okay, so when we look here, we can add to our collection of RMS quantities. We can define a RMS voltage and RMS electromotive force in the same way as we define our RMS current, and they will also be very useful here. And in an RLC series circuit, the average power of the generator is equal to the production rate of thermal energy in the resistor. So we can say that the average is equal to epsilon RMS times I RMS. So we're getting back to this version of it, times cosine phi, where cosine phi is something called the power factor. Okay? We did that already. Now, we want to look at our next. I thought there was something else on the power factor. This part here is the power factor. Let me make sure I'm not missing anything. No. And again, computing that stuff is really as easy as it looks. There's no secret trick to it. I'm going to turn on my light because it's getting dark in here. All right. Okay, that's easier for me to see the screen. Okay, that probably wasn't helping. So all these things are pretty straightforward to calculate. You just have to keep track of it. It's a lot of bookkeeping, and that's what you'll have to do. I don't know if you noticed the last example, but when we did our RCL series example, looking at the impedance and the current, it was really just keeping track of everything. So there's a lot of little things to keep track of, but none of it is that hard. But putting it all together can be, a little daunting, and keeping track of everything can lead to very quick errors. So you want to be careful. So let's go on to transformers. Now you remember when I started talking to you about AC circuitry and power, it was this ability for transformers to step up and step down voltage that made them ideal as devices for power transfer. All right? So what's really interesting is you have this transformer here. Okay, and you can see you have your AC source, and you have to think about what's going on here as you go through the coil. So the coil usually needs to be magnetically shielded, otherwise you have loss. But the bar here is a magnetic bar that can guide magnetic fields. So if you think about it, at one point you're shooting a current down here. But then you oscillate back the other way. So as you change and you're going back and forth through here, that's actually affecting the magnetic field through the bar. And that means that you have a secondary wrapped coil on the other side of the bar, you get an induced current. All right, so the current, so you have the field opposing the change, and the change will be going back and forth. So that will induce a AC current in this secondary circuit, all right, which you can deliver to your resistive load. And you'll have a voltage, a potential difference across the resistor from the secondary circuit. So you'll notice that you have your primary quantities here are V, N, and I, right? And you'll notice that they have either a P or S subscript. So P is for primary, S is for secondary, okay? And you can see that the secondary voltage will be equal to the primary voltage times the ratio of the secondary over the primary turns. Now the secondary can have more or less turns. And in fact, if you have, I just want to make sure they're not going to do it cleanly in the next slide before I start blabbing about it. Yeah, no, they're not. So basically, if you have NS is greater than NP, right? You're stepping up the voltage, meaning your secondary voltage is greater than your primary voltage, and that's a step-up transistor. If NS is less than NP, you're decreasing your voltage or you're stepping it down. That's a step-down transformer, okay? So those are your basic transformer equations. So if you want to look at energy transfers, let's see here. We can see that the rate that the energy transferred from the primary to the secondary coil is equal to IS times VS. Because we assume that no energy is lost along the way, conservation of energy requires that IPVP equals ISVS. That means that the total power, even though the voltage and current can change, right, the total power remains the same. So you don't get energy for nothing, but you can step up to a low current, high voltage circuit, and sometimes the voltages are in the millions of volts. You have tiny currents, and then you're dissipating because the current is so small across your thermal losses are much smaller, and you can transfer that power much easier. But you only have as much power as you created, right? There's no free energy from transformers. Okay, so keep that in mind. It can kind of look like it at first, but there isn't. Your input power is equal to your secondary power. And of course, we all know in the real world, there's always losses. So we have a transistor or a question, but I want to talk about this RS. So the equivalent, it says here that we can look at this equivalent resistance in the secondary circuit as the ratio of the turns squared over R. So I guess that's just something to look and calculate, because I don't even remember doing this part before. So first, we want to read the question. So a transformer on a utility pole operates at VP equals 8.5 kilovolts on the primary side and supplies electrical energy to a number of houses nearby at 120 volts. Both quantities bring RMS values. So these are RMS voltages. Assume an ideal step-down transformer, a purely resistive load, and a power supply factor. And a power factor of unity. So that means that the cosine phi part, cosine phi is equal to 1. So we know that. That's what the power factor is equal to unity. So that allows us to use our transformer equations, right? Which is V secondary equals V primary times N secondary over N primary. Yeah. So we have that. So if we have to look for, so it wants to know the turn ratio NP over NS. So you might have to do some massaging there to figure that out, but that shouldn't be too hard. Yep. Mm-hmm. I don't think the turn ratio, try inverting that, see if you get the right one, because it's supposed to be a turn ratio. Oh, okay, that makes sense. There you go. So it's probably close to 71. So that's usually you'd round up there to get in the approximate. So we'll call it 71. I guess you could make the argument that you should always round down because it would always be the highest integer. But when I look at what they do 71. I don't want to throw it off. So you should get around 71. And now it says, also if you're looking here, this implies that Vs over Vp is equal to Ns over Np, but that's not what it asked for, right? It asked for Np over Ns. So we look at, we can just say Vp over Vs equals Np over Ns. Okay. Well, that's the remember, that's the kilovolt thing. You have to divide that 8,500. Oh, you're right. 8.5 is in kilovolts. Yeah, 8,500 over 120. Yeah. Yeah. Oh, I see. Mustafa wrote 8.5 over 120. Yeah, it's in kilovolts, so it's 8,500 over 120. Okay. No problem. Hey, man, little mistakes are they're killing me. They're killing you guys. It's okay though, because you just have to be patient and go slowly. Okay, that's all that means. Well, it asks specifically for NP over NS, right? But we start with our transformer equation with an NS over NP. So I'm just doing algebra to solve here. Okay. Yeah. So it's inverted. Yeah. All right. So it says the average rate for part B, it says the average rate of energy consumption or dissipation in houses served by the transformer is 78 kilowatts. All right. Not in this apartment, let me tell you that. That is not true. I get 1.3 watts. After that, my power goes down. So that means each house gets 78 kilowatts, or maybe all of them get 78 kilowatts. I don't know. The average rate of energy in the houses served. Maybe it's so it's all the houses. Okay. So maybe my whole neighborhood gets my whole block gets 78 kilowatts. I can tell you, I don't get 78 kilowatts. I think each house should run. Usually it's about 1.5 kilowatts per circuit breaker. So if you count the circuit breakers in your house, that should give you an idea of how much maximum power you can draw in your apartment or your house. They're usually very big connections to the main power from the street to the building. It's just how do you want to run the wires up once you do that, which is the world I live in. So At least I don't have to worry about plugging too much stuff into one circuit because the whole house is one circuit. So, all right. So when we look here, it's asking what is the resistive, what the average, so we have that average bit is 78 kilowatts. What are the RMS currents in the primary and secondary transformer? Well, we know that, so it asks for RMS, and we know we've been given stuff in RMS, so we know that P average equals RMS, and you have your RMS voltages here, so you should be able to unpack that by just solving for I RMS equals P average over V RMS. All right. So see what you get there. All right. Well, I'm going to leave that as a cliffhanger because I just realized it's 7:55. So I've taken my picture of the attendance, and we'll call that a night. We're only about 2 minutes from where I wanted to be, but reviewing a little bit of our transformers won't be the worst thing in the world. So I'll probably just wrap this up and start with it next time so you can work on it, and I'll just wrap it up so you can check your answers. And then we are going to move on to Maxwell's equations, and we're finally going to be able to put together all the stuff we've learned in the course to make one framework for everything we've learned thus far. Okay? So sounds exciting. Keep in mind, now that I have you all here, it is the second test will be on the 20th, and we will have a review. I'm going to put together one of these Blackboard Collaborate rooms. We will have a room. I'll open it up. I'll make a special room at 3 p.m. on the 19th. That's what was asked for by students at the beginning of the class. Everyone seemed to be good with that. Now, what that means, though, is that you have to come with questions. I'm not going to just go over everything. I'm going to put up sample test questions over the weekend, so you'll have some time to work on those. And I'll put up everything, and we can, you'll just ask questions, and I'll answer the questions you have. And I encourage you to talk a lot amongst each other, too, and help each other out. And I'll just be there, to guide and to answer questions you might have. So I'm willing to do that for a little bit. All right? But keep in mind, we will have lecture at 5:45. So we will be lecturing. Okay. All right. I'm going to stop the recording so that I don't